check. Okay, well, I can shout for a bit, it's okay. So yes, if any of you were here to find out about FPU parts, I'm afraid Olga's poorly, so you'll be bored, or possibly fascinated. So we're going to talk about Debian and Arm instead, because there's things happening, and it's confusing, and this is a useful opportunity to explain it all to you. So I'll start off, I'm assuming this isn't a particularly ARM-specific audience, so we'll explain a bit about what all the names mean, because it's quite confusing. Does that work? Oh wow, yeah, that looks a lot better.
Better, isn't it?
Now I see why you said unmute it after you've flipped it on. Right. Okay. So, nomenclature. People will throw a lot of numbers at you in this talk, talking about Arm v7 and Arm v3 and Arm v this, that and the other, and it's a little bit confusing whether we're talking about CPU names or architecture numbers, because they're not the same, but they're quite similar. So I thought I'd just explain the Arm CPU cores have gone from Arm 2 to Arm 11 over the years. There was an Arm 1, but that was never put in any computers, so you can ignore that. And recently they got bored of calling them that, and the marketing department decided it should be called Cortex-A, Cortex-R, and Cortex-M instead, because it's cute. And they wanted to, rather than have 15 different sorts of Arm 11 with different options, which is where we were getting to, they've got three classes of CPU, A, R, and M. M is microcontroller cores, R is middle-sized, real-time sort of stuff, and A is proper computers running Linux. We mostly only care about Cortex-A here. So meanwhile, there's the ISA names, which is the instruction set, architecture, specification that each CPU implements. So to start with, these are the same. Arm 2 implemented Arm v2, but Arm 3 implemented Arm v2 as well, and so it's gone on. So the current Cortex series modern processors are all Arm version 7 architecture. So when someone says Arm 7, they might mean a really old Arm CPU from about 5 years ago, or they might mean the current architecture specification. That's why I thought it was worth making this point. So there's the Arm instruction set, but there's a whole lot of extensions to it, because Arm only specify the core stuff. Other people actually make chips with that stuff in, and it's up to those people which of the bits you can buy that they put in the CPU. Because they all cost money, you know, Arm charges for the core, and they charge you a bit extra for the floating point unit, and a bit extra for the thumb extensions, and so on. So you tend to get different chips with different bits of the specification implemented. We've had lots of them over the years. The original floating point unit from the dawn of time, Giselle, which was a subset of the Java virtual machine implemented in the core. Thumb 2, which are basically 16-bit versions of the same instruction set. Modern floating point called VFP, and Neon, which is a multiple SIMD unit for doing codec kinds of things. So like MMX instructions on x86. Important difference between Thumb and Thumb 2. Thumb was an extension to the Arm architecture which let you run most of the stuff in 16-bit mode, but you couldn't do everything. You have to switch back to Arm for some things. Thumb 2 you can do everything in, so it's actually a replacement for the Arm architecture, and these days in fact is encouraged because it's smaller and faster, so there's not much point using the old Arm instruction set anymore on modern stuff. So all this stuff about Debian Arm ports has to do with the ABIs and changes between ABIs. So the strength of Arm, the reason they've taken over the world, is that they make everything. You know, because they just implement the core and let other people decide which chips are needed in which markets and which options they should have and how fast they should blah blah blah. There's all this stuff, but the problem, the downside of all that is the heterogeneity of it all. It's all different. People make different variants. So there's an awful lot of different flavours of Arm, and that's a pain for us as software developers. So one of the variations you have is the ABI. Now Arm specify an ABI that you should be using, but there's quite a lot of options within the ABI, so it depends exactly which again, which you choose. So in the embedded world, this didn't matter because you always built everything for your particular target, and you picked some options, and that was fine. But in our world, where we distribute software to people, we have to decide in advance which flavors to use, and thus people like Debian have to pick an option and build everything for that. So the ABI is the Endianness, is it big endian or little endian machine, basic architecture, ARM, Intel, Spark, and the C library calling convention. So glibc defines a particular convention for calling functions, uclibc defines a different one, and so on. The actual set of instructions used is not, strictly speaking, part of the ABI. So again, on x86, if that's more familiar to some of you, there's a whole load of instruction set extensions like MMX. But as long as you don't use those, it'll run on the older machines as well. So that doesn't change the ABI, but you do need to make sure you don't use instructions that aren't implemented on the computer you're running on. So it's kind of ABI-ish. It's a little bit awkward. And again, CPU optimizations, you can order your instructions optimally for a particular CPU depending on how its pipeline works. It's just the same in x86 world as it is in ARM. You do things differently on R686 and 486, you do things differently on a Cortex A9 than you do on an ARM v7. But again, that doesn't change the ABI, it just changes how fast that particular code goes on a particular chip. And if you don't know which chip is going to be running on in advance, then you pick an option which isn't particularly terrible on any of them. And more to the point, doesn't use instructions that some of them haven't got, because that's really slow. This particularly matters in the floating point area. So the original ARM CPUs did specify a floating point unit called FPA a long, long time ago, circa ARM 3. Actually, probably earlier than 96, ages ago. But in practice, nobody ever used it. So there was this, there were floating point instructions, but on almost every chip made for the next 10 years, those instructions were not implemented. So they were always emulated. We'll get onto the effects of that in a bit. In the meantime, other people who bought architecture licenses, like Intel, put their own stuff in. So Intel did IWMMXT, which is a bit like MMX, but implemented on the ARM architecture. Cirrus did the strange Maverick Crunch thing, which basically is some instructions for playing MP3s faster. I think it's fairly specific stuff. Since version 5 of the architecture, we've had VFP as an option available for people to put in their CPUs, but they didn't always. Since V7, we always have VFP. So pretty much after 15 years, we're back to a state where ARM CPUs have floating point units in them, and you can expect to be able to use them. It's like a normal computer. Neon is the other thing, which is current, which is this simmed unit, and again that's usually present in a modern CPU, but not quite all of them. Specifically not Tegra 2, which is one of the things you can actually get right now. So, because of all this, the floating point use on ARM has been interesting. So normally you just put floating point instructions in the instruction stream like any other instructions, and they get used. That's kind of the way, especially x86 people expect the world to work. But as I say, and that was the way it was done to start with, the old original ARM port. But the problem was that because there never was a floating point unit, those instructions were always trapped as something you can't execute, and then you emulate it in software. And obviously, software emulation of floating point is slow. It turned out that the trapping in the kernel of an instruction abort, jumping off over here, emulating it and jumping back again, was even slower. And there's hundreds of instructions every time you executed an instruction. So that's not ideal. There's also soft float, which is a way of dealing with this problem. So rather than just put the instructions in the stream, you you compile the stuff so that you use the emulation directly. So the compiler goes, all that's going to happen is this instruction will get trapped and emulated, so let's just put the emulation in straight away and not actually run any floating point instructions. Which works much better if you know you're not going to have a floating point unit anyway. Hard flow is basically normal, i.e. just run the instructions as if there was a floating point unit. And there's the soft FP variation on this, which is use the calling convention for the we haven't got a floating point unit, but still pass them on to the real one because in fact we have got one. The point being that that's compatible with the mode where you haven't. So the compiler provides all these options and they're incompatible. You can't mix them together without taking enormous care. So people making distributions have to pick what they're going to do. It's actually even more complicated than that, but you don't really want to know this, I don't think. Within the V7 architecture specification, there are three different ways of calling, or there's 2 different ways of calling, I think, and another way of the details. So VFP, there's been version 1, version 2, and now we're on to version 3. You can either use 16 registers to pass functions, pass things to functions, or 32 registers, and there's a half precision mode as well, even quite short, if that makes. Fortunately, the Neon unit uses the floating point registers, so that doesn't add incompatibility in the calling convention. It's just that you don't want to use it if it's not present. I hope all that made sense. It confuses me in the past. The other important aspect of the ABI is Endianness. So ARMs for a long time have been switchable. Basically, when you start it up, you can choose to run in big endian mode or little endian mode. They were ever so pleased with that, because the way the architecture works, it was really trivial to just set a little bit and the whole thing would switch around. But in fact, they wish they'd never done it, because it just caused aggravation. Very few people use the big endian mode on ARM. It's almost always little endian. The only people who care are network processor people making routers, and there's a specific chip series made by Intel IXP which was designed for that. And it is a bit quicker if all you ever do is shift Ethernet packets, if you run the whole thing in big endian mode, because you don't have to keep swapping them around to work out the numbers. But this is a fairly minor performance gain, especially on modern CPUs, because they've got a swap instruction to do just that, so it's a single cycle anyway. So mostly people will tell you not to do that these days. And I don't believe any significant distributions or operating systems are running big endian anymore. So, onto the actual ARM ports that implement all these various things. So the ARM architecture was first released in TODO Vintage, which is now quite a long time ago. That's about when I got involved in this stuff. I've been doing ARM and RISC-OFs before that. And it's just about to be declared finished. So nobody cares about old ARM anymore, except for people with incredibly old hardware like netwinders, which of course is still working. It's a bit unfortunate, but it's breaking already because it's not interesting. ARM released the new version, I'll mention that in a moment, about 6 years ago, so this really is old hat. Implements what we now call the old ABI, which was originally called the APCS, for ARM Procedure Call Standard, which basically came from RISC-OFs and did slightly funky things. And assumed that you had one of these FPUs that never existed, pretty much. So it was always very slow if anyone foolishly tried to run any floating point code. So back at Lenny, we did the ARMEL port, which is essentially the new ABI that ARM specified for everybody. So that's Linux people, Windows people, and Symbian OS people, as it was at the time. An improved ABI for newer CPUs and the way the world works these days, and all these dealing with the floating point problem and stuff like that. So ARMEL is almost certainly what you're currently using. Debian people are still using. So that goes back as far as ARM v4t, which is now quite old. There are still ARM v4 CPUs about, most noticeably strong ARMs. So this nomenclature, by the way, so the way ARM used to specify all the options that you could include was letters on the end of the architecture name. So you get a v4. V4t means it's v4, but it supports the thumb mode. Now you get a an ARM9TJZE or something, which did Thumb and Giselle and something else, which was why they changed the Cortex naming, because this was getting out of hand. So on Armhf, we picked the soft float option because at the time there were no CPUs with FPUs, and it was incredibly efficient running in the emulated mode. And the point is that if you have a floating point unit, it's still reasonably efficient to run that. So this port will work on pretty much anything that you can still buy, but obviously on newer CPUs it is nothing like as fast as it could be because we're not using any of the shiny new stuff. Just a little bit of confusion, Ubuntu Armhf is not the same. They've moved forward to V7, Thumb 2 and the soft FP option, which is slightly different. So if you stick Ubuntu Armhf binaries on a Debian Armhf machine, it probably breaks. Don't do that. There was an ARMhf port, so that was the big Endian ARM, based on the old ABI, ARMv3. That was pretty much done because the NSLU2 had a proprietary Ethernet driver in it, and the only way to get it to run was in the big Endian mode it had been supplied with. I guess that's an IXP chip. So, you know, the only way, or the best way to get Debian running on it was to rebuild the whole damn thing for the other Endianness, which Leonard Buitenhek did pretty much solo, scary man. But this is basically to be ignored. We don't care anymore, and it was only for the old ABI anyway. Confusingly, of course, you'd expect ARMhf to be the mirror of Armhf, but in fact it's not. Now we're on to modern times, and I can pass you on to Zumbi to talk about this. So old, you see, you get history from me.
Hello. Hello. Well, we have new devices in the market, like this netbook, which has an ARM processor. We have mobile phones, and we have CPUs with floating point units, and we want to be able to run an operating system fairly optimized. So we based on Debian. What's going on here?
Wow. Doesn't like you. All we've got is like oops and bad stuff.
Then,
sorry.
We got a set file here. But it's going to take a while to get it back. But basically, there was this company interested to run a hard float ARM port. So they started to bootstrap the hard float port for Debian, and we have been doing this work lately.
What are you going to say now, aren't you? So maybe a short pause, a little intermission in this talk while we reboot. I've never seen that before. We're halfway through a talk. The computer explodes because you changed presenters. It's just weird.
Maybe it's not comfortable.
There's no Endianness change.
It's irritating.
Yeah, it didn't translate.
Or it doesn't like you.
We need to make the boot faster.
Perhaps it depends on the
Unfortunately, I've got nothing on my TV now. Where did all those web browser windows go? Yeah, I know.
Yeah. So basically, we are proposing a new architecture which we call Armhf, or hard flow, and it has thumb 2 and it is thumb 2 which is faster, hard flow which is faster as well, and it's ARMv7 optimized, which is the netbooks and mobile devices with internet connectivity are shipping nowadays. For more information, you can check the wiki. And there were some tests done on performance by Clean Adams, and basically it's a Vorbis gain test. And we can see running the test on Armhf, which is soft float, versus Ubuntu Debian soft FP. We got this performance improvement, which is encoding MP3 gets, or OGG gets 15 minutes, almost 16 minutes for Armhf port, while you get around 10 minutes for Ubuntu. And then Armhf versus Armhf Debian, you can encoding it's 16 minutes, and then for a hard flow, taking benefit of the floating point unit, it goes on around 7 minutes, almost 8. There was Konstantinos Margaritis. He's been doing a lot of the work on the Armhf port, and he had a benchmark, several benchmarks, and he ran GLX gears, which is just a test suite which uses a lot of floating point, and you can see there's also an improvement for hard FP. So summarizing might be something which can be interesting to have, which we can gain around 40% on pop rate.
I think I got that wrong. I think it was 200% on pop rate or something. It was something else that was 40%. So there are exceptional cases where you've got enormous amounts of floating point and lots of function calls can go enormously faster. Things that are just some floating point go somewhat faster.
I would like to ask, what is the difference in the integer performance?
Integer performance.
Integer?
Yeah, we have it here.
Oh, sorry.
Yeah. Well, the Vorbis tests, if you want, they're more complete. It's in this mail address, so you can have a look. The Konstantinos tests are published on this site, and he ran this benchmark. So we basically proved that it's 30 to 40% better performance on hard flow if you use a floating point. But if you use integer, then you get 1% performance. So it's not around, or 0.5%, which is very few, very low.
So essentially, there should be no difference in the non-floating point performance just due to changing the ABI.
There should
Depends entirely on your CPU.
There should be difference between the thumb and thumb 2 now.
Oh, sorry, yes, that's true. There should be thumb changes, and potentially there's obviously if you optimise for V7 rather than V5 or Cortex A8 or whatever, then you would expect some performance gains there. It's difficult to make direct. I guess you could build for V5 and run it on a Cortex A8, and it should go slower than if you optimise. But yeah, I'm not quite sure what those numbers are. Lord probably knows. Okay. Generally, we shouldn't expect any of this to be slower. Each of the aspects makes it a bit faster, and some of the floating point different stuff can make an enormous difference. Yes. And increasingly that matters on desktops that are using OpenGL and all this shiny SVG squirty stuff that we have to have these days.
One thing to keep in mind is that if you're building, one big problem in measuring that is that if you're using common benchmarks like the Embassy or the spec benchmarks, things like that, because they are monolithic applications, the compiler will actually use half float even if you say soft float. So when you're comparing soft float with half float, the compiler will use actually the same code in both cases, so the benchmarks will look almost identical. It will only use the half float calling conventions if you have an ABI and a shell library and you're doing calls, something like that. That's the only case where you see a difference. And it's something which harmed the measurement of the performance benefits we could reap off of Armhf for a long time, because people were looking at benchmarks which would be built as like a monolithic executable which was calling into its own functions, and it was not visible what kind of performance benefits you could use. When you're using it on a system, you get library calls across many different types of libraries. Even if float is not so common, it's still a benefit.
Okay. We started to bootstrap Armhf and it's on Debian ports, and it's this green line here. So we got around 85% of Debian archive build, which is pretty much usable right now. And there is still work to do. You can find on the wiki address. And then we plan to do a mass backfilling into Debian and try to maybe upload packages for supporting this architecture. And there is a couple sponsored sprints to do this. In February in Cambridge we're meeting at ARM Holdings, and then in April we're meeting at Genesi in San Antonio, Texas, to keep working on this board.
One thing that's a useful benefit of this work is that effectively Ubuntu, Debian and MeeGo at least will all be doing the same compatible stuff, which should all improve our lives generally. Pretty much everyone is now making a jump to V7 or later for all this. So in Debian it's important that we keep the Armhf port around for everything else that isn't new or high performance. Some of those people won't really be running optimized code, but by and large that will work everywhere else. So those two ports should cover all ARM machines for some while until we have to move along again. I hope people agree with that. It's one of the things that will get discussed at the sprint that's happening in a couple of weeks' time. If anyone doesn't know about that and is interested in ARM stuff, that's the place to come. But obviously, moan now if you have a machine that you feel is being ignored and hopelessly unsupported by what's going on. Yeah, you can. So, another aspect of this that's a bit complicated is, as well as the ABI, which is incompatible changes, so Armhf and Armhf and old ARM are all different, and you can't mix binaries packages from those distributions. There's all sorts of stuff you can do within an ABI that's still different and optimized. So, depending what CPU and what functional units you've actually got. We have this problem with other architectures as well. So, and by and large, we deal with it within Debian by dealing in specific packages by making multiple variants. So, mplayer builds mplayer i386 and mplayer i686, and we have libc 486 and 686 and so on, which is a bit clumsy, really. But it works, and it works because there aren't that many packages where you really care enough to do the optimized version, so you can do it specifically in those packages. But one day we have this vision of a world where maybe it would be possible to just optimize the stuff you need to optimize, but just put the packets in packages in an extra repo. If it wasn't, so you didn't have to rebuild the whole thing, do a whole 17,000 package Debian port just to change some minor aspect of your optimizations. But you could still make packages, put them in a repository, and have apt do the right thing and go, oh, I'm running on a such and such, and these optimized packages are available that use Neon, so let's install those and run them. But if they aren't present, you'll get the standard stuff. So there has been some work on how this might be done. It's generally referred to as flavors. So it's which CPU actually optimized for and which extra bits were included. But basically, at the moment, there isn't an easy way of doing this, and it's one of the things that I'd like to see happen over the next couple of years. And hopefully, Linaro might do some of that. We'll see. So yeah, if anyone has bright ideas about how to put that metadata into packages and what exactly should happen, we have a mechanism at the low level in GCC and the linker to basically do this right. You can already have it fall back from more specialized directories to the default architecture thing. So if you've installed some optimized binaries, they'll get run. If they're not there, it'll just run the base stuff. So we can make packages that put files in the right places and it just works, but we don't have mechanism in dpackage and apt for defining how that would be done, which packages you get when, and how you decide which ones to get, and all that sort of thing. So there's a whole load of guff here about how this all works at the GCC and linker level for anyone who cares. It's quite scary stuff. Right, yes, that's pretty much all we have to say, I think. Are there any questions? Oh yes, not quite, I forgot.
Well, there's sponsors to Endianness and Arm, and a sponsor is the sprints, and some of the people working on this is employed by these companies, and also Linaro is involved, and Canonical. So we want to thank Konstantinos Margaritis, who is Endianness employee. He couldn't come. He should be doing this talk actually. Debian Arm and lots of individuals which are around. And Linaro GCC toolchain people, which is the one we use to bootstrap the Armhf port, because we use the GCC 4.4 and doesn't have hard float support unless you use Linaro's patches. And if you want to send any comments, you just use the Debian Arm mailing list. And just remember to have fun. So if you got any questions or comments, yeah.
Does it also support becoming quad-core ARM processors from ARM?
That should already be working, yeah. I think basically you need to have eglibc rather than glibc for the multi-core stuff to work, and that's been done a while ago. I hope it's all in and working. Oh, so?
Yeah, so we already support Pinboard, which is dual-core Cortex NI, and quad-core Cortex NI is just the same thing.
Okay.
Just depends whether the kernel support for your board. But, yeah. But the user space, general purpose user space is mostly ready, but some libraries are lacking. Might be inefficient on SMP, or might be lacking some proper safeguards, and notably in non-Linux, non-desktop user space like Android, there are lots of libraries which still have SMP issues.
There's probably plenty of bugs, I think. Yeah.
TODO 3 is fixing that a lot.
So this has been done a while ago, and now actual chips are coming out, so people actually get to use it all and find out what's still left that's broken. But by and large, yeah, it just works.
We don't see ARM in servers.
I couldn't possibly tell you. It's top secret. Not too long, I hope. Somebody else that
you should expect SMP by default in the future. Like it should be common to have lot of SMP hardware. Just like pretty much all laptops you get nowadays have SMP as well.
I was using the ARM on an SLE2, and it broke because it changed to Armhf with squeeze. Should I expect that break with the
Armhf? Yes.
Unfortunately, upgrading between architectures is not something we do very well. There isn't a nice way of saying, change to something incompatible.
My com was multi-arch.
Yes, that's true. I guess when we have our multi-arch stuff working, it will be a lot easier to implement something that actually would do a smooth. It's very difficult to suddenly change, because it's got to be a moment when you stop running anything like that and start running everything like this. Don't accidentally jump back into some old code, because it'll just blow up.
Well, I was asking, should I expect the same thing today, because the squeeze stops and there'll be no more.
So the old Armhf port will stay around for some long time, until there's no more Armv5 CPUs in use. So you can carry on using Armhf for quite a few years yet. I don't know how many. 6 maybe. When your slug will be really, really slow by then, and you'll probably want something better.
So 2 megs of RAM. So
yeah.
Did you say that the netwinder support falls off with loss of the ARM port?
Yes, because it's V4, and so you can run EABI on V4, but you can't have thumb interworking. People want thumb interworking, and we couldn't. In fact, the GCC fixes have now been done, so you can build a GCC which supports V4 with thumb interworking. But the problem is that puts an overhead in every function call for everybody. So that was where the cutoff went.
Yeah, that's
so there isn't anything to. It's not that it's impossible.
No, I was just trying to understand.
Exactly, it's that it wasn't a sensible choice for Debian, which is a pity because there are still wider machines and people.
I have one that works.
Exactly, I've got one. But yeah, basically that's. And what's the point? There's still strong arm stuff that was being sold up until about a year ago. It's not quite as dead as we'd like.
It gives me an excuse to get the lending merch.
And in fact, it's worse than that because there's a Chinese outfit who produced a new ARM 7 core, which is V4 and not V4T. So there's some obscure NAS machines you can get with this thing in, which people bought in 2008, and they're V4. So if anybody wants to support a V4 thing, then more power to them.
Did that once.
But it's not quite worth it, I don't think.
Do you expect to write the requirements of the Armhf port? Is this something you recommend?
Yeah, I don't know how much V4T there is in the world. There's an awful lot. There's mostly, I guess not very much of it's running Linux.
Yeah. I think V5T might be more useful.
It would.
More Armhf.
I guess it's always difficult being Debian. We don't actually know what people run our stuff on. It's very hard to know when there really are only 20 people left and we can drop them, or 200, or whatever the limit is. It would be really useful if popularity contests reported machine architectures. And then we would know. Well, at least we would have some data rather than none.
That sounds like an easy thing to add.
Yeah, it is. I keep thinking this would be a good idea, but I haven't done anything about it. Got a maintainer here, haven't we? So yeah, you're right. At some point we'll move to V5. I don't know when. I guess we haven't just done it now, so probably Wheezy. A rough guess. Any more for any more? We'll go and have lunch. Thank you very much.